Good morning, students. Today I am going to discuss the second session connected with electricity and electromagnetic theory. In the previous session, we discussed about what is magnetism, what is the expression for the magnetic force or mechanical force, and the characteristics of that magnetic force or mechanical force, and later the Lorentz force equation. Before that, what is Lorentz force? Then what is the expression for Lorentz force and the terms explanation. Later on, the characteristics of the Lorentz force. These concepts were discussed in the previous discussion. In addition to that, I am going to brief about the distinction or differences between magnetic flux density and magnetic intensity, or magnetic field and magnetic intensity or magnetizing force. Today, in this session, I am going to discuss about the concepts like differences between B and H, then origin of induced EMF in a conductor moving in a magnetic field. And later on, we are going to discuss the characteristics of the magnetic lines of force or B lines or magnetic field lines, and divergence of B is equal to 0. The divergence of B equal to 0 concept is also discussed in the previous semester. Once again, here we are going to review that concept after discussing the characteristics of the magnetic lines of force. Now I am going to give the differences between B and H, that is magnetic field B and magnetic intensity H. The first point is the definition itself, one of the differences between the magnetic field B and magnetic intensity H. First point, the total flux crossing a unit area placed normal to the magnetic field at a point. That is what we call the magnetic field or magnetic flux density. The total flux crossing a unit area placed normal to the magnetic field at a point. Here in the case of magnetic intensity, it is defined as the degree to which a magnetic field can magnetize a material. The degree to which a magnetic field can magnetize a material is what we call magnetic intensity or intensity of magnetization. The second point is here magnetic flux density depends on both permeability of the medium and current. Magnetic flux density depends on both permeability of the media and current, but the magnetic intensity, it depends only on current. It does not depend upon the nature of medium where we have to measure the magnetizing force or magnetic intensity. Then another difference is the SI unit of B is Tesla or Weber per meter square. Here the SI unit of magnetic intensity is ampere per meter. These are the differences between B and H. Next we are going to discuss the concept of induced EMF. What is EMF first? Electromotive force. In the PU classes we came across the definition of EMF before discussing the Faraday's laws of electromagnetic induction. There we come across this type of concept, that is electromotive force. The scientist Faraday itself, he introduced this concept, and he measured the amount of electromotive force induced in a circuit. So now we are going to give the definition of EMF, and later on we are going to discuss the origin of EMF or induced EMF in a conductor moving in a magnetic field. Whenever the number of magnetic lines of induction or lines of force or magnetic flux through a circuit changes, an induced EMF is produced in the circuit. Whenever a magnetic flux linking with the coil changes or a circuit changes, an EMF is induced in the circuit or a coil. This is in accordance with Faraday's first law. Okay. The magnitude of the induced EMF is proportional to the rate of change of magnetic flux. The time rate of change of magnetic flux will decide the magnitude of the induced EMF in the circuit or a coil. That is given by the measurement of EMF is given by Faraday's second law. If d phi is the change in magnetic flux in a time dt, then according to Faraday's law, the induced EMF is given by E proportional to d phi by dt, or E is equal to minus d phi by dt. Here, the negative sign indicates that the direction of the induced EMF is opposite to the rate of change of flux linking with the coil. That is represented by negative sign. It is also called as Lenz law. The scientist Lenz, he gave this explanation. He tried to explain the direction of the induced EMF with respect to the magnetic flux linking with the coil. Okay, change in magnetic flux linking with the coil. This is a PU concept. Now we are going to discuss origin of induced EMF in a conductor moving in a magnetic field region. For that, let's consider a straight conductor, okay, or conducting rod, say PQ of length L. Okay, in this figure, okay, in figure 2, there is a conductor whose length is, let it be taken as L, that is placed in a magnetic field such that the direction of the magnetic field is perpendicular to the length of the current carrying conductor. That is represented by the cross marks. Okay, if you observe in figure the plane of the conductor, we are going to mark some cross. Okay, those represent the direction of the magnetic field is perpendicular to the length of the conductor or plane containing the conductor. Keeping the magnetic field constant and moving a conductor through it, okay, gives an EMF in the conductor. The EMF induced is called motional EMF. If you move the conductor in a direction which is perpendicular to the magnetic field, if the length of the conductor, if it is perpendicular to the direction of the magnetic field, then what happens? The magnetic flux or the magnetic lines of force linking with the conductor changes. The changing magnetic flux will induce or set an EMF inside the conductor. For that, consider a uniform magnetic field B perpendicular to length and perpendicular to plane of paper. Okay, here the magnetic field B is perpendicular to both the length of the current carrying conductor and as well as the plane where the current carrying conductor is placed. Okay, let the conductor move with a velocity v. Okay, here we found that the electrons have sidewise velocity along the direction of motion of conductor because they move along the direction of motion of the conductor. This velocity with a vertical B resulting a force on the electron directed along the conductor. Consequently, the electrons are pushed along the length of the conductor. They in turn complete the circuit. We call this net integrated push as induced EMF in the circuit. Okay, here the velocity of motion of the direction of velocity of these electrons is sidewise with respect to the length of the conductor and direction of motion of the conductor. Here the conductor is moving in such a direction that which is perpendicular to the magnetic field. It is perpendicular to magnetic field. Thereby here the velocity of the electrons is sidewise with respect to the length of the conductor and magnetic field. They both which is perpendicular to both magnetic field and the length. Thereby the magnetic force or mechanical force exert on these electrons would be along the direction of motion of the conductor, that is along its length. Then whatever the net integrated push experienced by these electrons inside the conductor along its length, okay, is called as induced EMF. So the measurement of this induced EMF can be done by using the concept of Lorentz force. Okay, here from Lorentz force equation we may obtain the expression for the mechanical force or magnetic force experienced by the electrons moving inside the conductor. Here only magnetic field is present now, the electrical force is absent. Then F is equal to Q into E plus B cross V. That is the expression for magnetic Lorentz force. In that, if you neglect electrical force, then the expression for Lorentz force becomes F is equal to BQV. Sine theta is there, sine theta equal to 90 degree, thereby sine 90 is 1. The F is equal to, this is the maximum force would experience by the electrons inside the conductor moving in a magnetic field. Thereby, if we define the work done, then work done is equal to force into displacement. Here, displacement nothing but the length of the conductor itself. Electrons can move one end of the conductor to another end of the conductor now. Thereby, the displacement is taken as length. So, work done is equal to force into displacement, that is Fl, that is equal to BQV into L. Now, work done per unit charge. We define work done per unit charge, that is what we call EMF. The amount of work done required to bringing a unit positive charge once around the circuit is what we call electromotive force. Thereby, work done by charge gives BVL. That is nothing but what? The induced EMF in the conductor. Therefore, E is equal to BVL. This is the expression for induced EMF. It also be expressed in terms of integral, the line integral, that is E induced is equal to the line integral among the closed path V cross B dl. That is another notation is there. Okay, in integral form also we can express this induced EMF. Okay, later I am going to share my handwritten notes in that integral version is also there. Next, characteristics of magnetic lines of force or divergence of B is equal to 0. First we have to focus on the characteristics and later we are going to summarize divergence of B is equal to 0. First characteristic is the lines of magnetic fields are closed curves around the current element. The lines of magnetic fields are closed curves around the current carrying element. These are the continuous closed curves. Okay. Thereby, we observed later, we are going to discuss that one. Magnetic monopole does not exist in nature after discussing the UV equal to 0. This is the characteristic. Next, the total number of lines entering a volume must be equal to total number of lines leaving the volume under consideration. If you consider a finite volume in space where these lines of force are distributed, okay, then if you observe the total number of lines of force entering to that volume under consideration, then the total number of lines of force leaving that volume. There are no sources or sinks to the magnetic lines of force. Unlike electric field, okay, there we found that there is separate source and sinks are present. That is, positive charge act as a source and negative charge act as a sink. But in the case of magnetic field, we found that there are no sources or sinks to the magnetic lines of force. Magnetic poles are always exist in the form of dipole. Magnetic monopole does not exist in nature. Thereby, there are no separate sources and sinks were present in the case of magnetic field. The divergence of a vector signifies the starting or stopping point of the vector. The divergence of a vector signifies the starting and the stopping point. Again, source point and sink point. We should expect that in the case of magnetic field, div B is equal to 0. Divergence of B is equal to 0 because there are no separate source and sinks exist in the case of magnetic field. So, magnetic monopoles do not exist. Hence, divergence B is equal to 0. Div B equal to 0 is also discussed in previous semester. It is important result after discussing the divergence of the magnetic field. That result is magnetic monopole does not exist in nature. So, the few characteristics of magnetic lines of force and divergence of B is equal to 0.